So here we got a nice IMO 1976 polynomial problem, and the problem is that we are given p1 of x equals x square minus 2 and pj of x equals p1 applied to pj minus 1 of x, where j starts from 2, 3, 4 and so on, and we have to show that for any positive integer n, so n is greater than 0, the root of the equation, so the equation is Pn x equals x, are real and distinct. So to solve this problem, I'm going to use the method of substitution. So if we look into this equation, which is p1 of x equals x square minus 2, and substitute the value x equals 2 cos of theta, we can simply say that p1 of x equals 2 cos of theta whole square minus 2, and after solving this we'll get 2 cos square theta minus 1, and this is our cos of 2 theta. Similarly, we can simply find the value of p index 2 of x, which is p1 applied to p1 of x by this expression, and now we can say that p1 and the value of p1 of x is twice cos 2 of theta, and we can simply apply this definition of p1, which is x square minus 2. So 2 cos 2 theta whole square minus 2, and after solving this we'll obtain 2 multiplied by 2 cos square 2 theta minus 1, and this is our 2 multiplied by cos 4 of theta. And now we can simply generalize this result. We can say that Pn of x equals 2 multiplied by cos 2 raised to the power n theta, because if you see here, when the index was 1, then we'll obtain 2 raised to the power 1 here, and when the index was 2, then we obtain 2 raised to the power 2 over here. So for general n index, this would be 2 raised to the power n. And now we can simply solve the equation Pn of x equals x, which is same as writing Pn instead of x 2 cos theta equals 2 cos theta. And now we know that Pn of x is equal this, so we can simply substitute the value 2 multiplied by cos of 2 raised to the power n theta equals 2 cos of theta. Now we can simply cancel these 2, and we'll obtain cos 2 raised to the power n theta equals cos of theta. And we have to solve this equation. So after solving this, the result would be, since we know that if cos theta equals cos of alpha, we know the solution is theta equals 2n pi plus or minus alpha. So we can simply use this result to solve this particular equation, and we'll obtain 2 raised to the power n theta equals 2n pi plus or minus theta. And this simply implies that 2 raised to the power n theta plus or minus theta equals 2n pi. So this would simply implies that theta equals 2n pi divided by 2 raised to the power n plus or minus 1. So here we got the two forms. First is 2n pi divided by 2 raised to the power n plus 1, and the second is 2n pi divided by 2 raised to the power n minus 1. So this is the real and the distinct solutions of the equation Pn of x equals x. So the next problem is an inequality problem, but we are going to solve this using the polynomial. So let's consider this inequality expression, which is a square plus ab plus b square is greater than 3a plus b minus 1. So I'm going to shift this in left hand side, so we'll obtain a square plus ab plus b square minus 3a plus b minus 1 greater than or equal to 0. And now I'm going to consider this as a function f of a, function in term of a. So a square plus ab minus 3a plus b square minus 3b plus 3. So we can rewrite it as a square plus b minus 3 multiplied by a plus b square minus 3b plus 3. And if you see, then this is the quadratic equation where this is the constant term c, and we have to prove that f is greater than or equal to 0. So for this condition, if quadratic is greater than or equal to 0, the discriminant must have to be smaller than or equal to 0. So we can simply say that discriminant is b square minus 4ac is greater than or equal to 0, is smaller than or equal to 0. So the value of a is 1 and the b is this, b minus 3, and the constant c is b square minus 3b plus 3. And make sure the b, this b is from the standard form of quadratic, which is ax square plus bx plus c. So there is a difference between this b and this. So I'm going to put the values. So we'll obtain b minus 3 whole square minus 4 into 1 into c b square minus 3b plus 3 smaller than or equal to 0. And after solving this, we'll obtain b square minus 6b plus 9 minus 4b square plus 12b minus 12 smaller than or equal to 0. We can simplify this and we'll obtain minus of 3b square after solving this, and plus 6b and minus of 3 smaller than or equal to 0. And we can simply take 3 common. So 3 multiplied by minus of b square plus 2b minus 1 smaller than or equal to 0. And we can also take minus, and we can also take minus sign common. So we'll obtain minus of 3b square minus 2b plus 1 is smaller than or equal to 0. And this is our b minus 1 whole square multiplied by minus of 3 smaller than or equal to 0. And this simply implies, since we know that the square term would be always positive, so this whole expression is less than 0. So this simply implies that our function f is smaller than, is greater than or equal to 0. So this simply completes the proof, and this implies that a graph of this function f must be something like this or like this. So there is two cases, first and second.